This work presents how to use corners to see around corners using edge-resolved transient imaging. Non-line of sight imaging is the goal of reconstructing a scene that's outside line of sight, such as around a corner, shown here. This imaging modality could potentially be used to help autonomous vehicles anticipate hidden obstacles or to find unseen survivors in search and rescue applications. There are two general approaches to non-line of sight imaging that have been introduced in the past decade. Active methods such as references 1 and 2 probe the hidden scene by actively illuminating a visible relay surface and using time-resolved detection of the reflected light. They then try to invert the transient light transport to recover the scene. These methods typically require scanning a laser to many locations over a large area of a relay wall, which may not be present in many environments. Because the signal detected from the hidden scene is extremely weak, active methods demonstrated on large-scale scenes rely on high-powered lasers and retroreflective targets. Alternatively, passive methods use the global illumination of the hidden scene, but because they use standard cameras with no temporal information, recovering the hidden scene is an ill-posed problem. Many passive methods, including references 3 and 4, use the occlusion of some light paths to improve the conditioning of the inverse problem and aid recovery. In this work, we combine the best aspects of both methods into what we call edge-resolved transient imaging. Like in the passive corner camera work, we use a visible vertical edge to separate light from the hidden scene according to the angular position. In our case, we propose a Helmholtz reciprocal dual where illuminating different locations along a small arc controls which part of the hidden scene is illuminated. You can see from the animation how this illuminates an increasing portion of the scene. Our illumination source is a pulsed green laser, and we use the time resolution of a single photon avalanche diode, or SPAD, to acquire a histogram of photon detection times for each illumination position. Since each position only illuminates a small additional wedge of the hidden scene, we can isolate this wedge by taking differences between subsequent histograms, which yields the transient response from objects in only that wedge. We have seen that using the vertical edge helps give angular resolution, and that time-resolved sensing allows us to recover radial information from the time of flight. However, there is no similarly straightforward way to resolve ambiguity along the vertical dimension. We first constrain our scene representation in order to make some sense of the data that we acquire. In particular, we assume that the scene consists of a ceiling plus vertical planar facets that start at the ground and span the solid angle of a wedge. In addition to the distances to each planar facet, we also parameterize them by their height and their normal vector, which are encoded in the temporal response profile shape and duration. Because we constrain the facets to extend up from the ground, we call this representation 2.5 dimensional. Taking into account that our acquisition configuration is approximately confocal, we can compute a closed form approximation to the transient response that a planar facet with a distance ρ, height eta, albedo alpha, and orientation angle phi, as seen on the diagram here, would generate. We note that our light transport model for each wedge is nonlinear, which accounts for the fact that closer objects may partially occlude objects that are further away. There are several challenges we face when trying to recover a hidden scene. For instance, we do not know in advance the number of objects and hence the number of facets that should be at each angle. In addition, the differences between Poissonian histograms may have very large noise variance, even if the mean itself is small. To improve the recovery, we make note that the floor positions of objects describes a 1D manifold. Furthermore, the parameters of neighboring facets are highly correlated. To reconstruct the hidden scene, we use a reversible jump Markov chain Monte Carlo algorithm inspired by state-of-the-art methods in line-of-sight LiDAR. This algorithm aims to maximize a posterior distribution to give the most likely configuration of facets given the acquired data and priors on the hidden scene, such as those mentioned above. The algorithm takes advantage of the fast evaluation of the light transport model to yield reconstruction times of around 100 seconds on a laptop computer. Here we show reconstruction results for 3 experiments. In each case, we have a large-scale scene of about 3 meters in each dimension with up to 2 objects in the middle of a room. Each acquisition uses only 45 illumination positions for an extremely small scanning radius of 1.5 centimeters, and yet recovers a 180-degree view of the scene. We can see that the reconstruction is generally matched the true scene layout captured by a laser distance meter, and objects like the mannequins and staircase confirm that we can measure facet heights with a precision of less than 10 centimeters, even though the acquisition has no inherent source of vertical resolution. For more details on this, please see our archive paper in reference 6. Thank you.